We will then move on to our third talk, which is by our own Dr. Jianwei Huang from Rice.
Thank you.
Thank you. And he will tell us about orbital selective correlations in iron-based superconductors and other materials. So, Jianwei, go ahead.
Yeah, okay. I see the right screen.
Looks good.
Okay. So thank you, Ming, for inviting me to present our recent results in this very nice workshop. So I'm Jianwei Huang from Minus Group at Rice. So today I'm going to mainly talk about these optoselective electron correlations in the iron-based superconductors and also one case beyond. So let me first thank our collaborators. Our RPES studies has mainly supported by a lot of benign scientists from the synchrotron, including the SLAC, AOS, and Brookhaven National Lab. And also our later RPES results were obtained in my PhD advisor, Professor Xinjiang Zhou's group, performed by his former student, Yongjin Cai. And we also have theory collaborators, which Qimiao and Boris Jakobson's group at Rice, and Rong Yu's group at Renmin University, and Jianxin Zhu at Los Alamos National Lab. And I think especially Qimiao's group, they not just simply provide the theory input for our data, but also actually lead uh, our research directions in many different ways. And also our samples from Pengchen Dai's group at Rice and Genda Group's group at Brookhaven National Lab and Junhao Zhu's group at the University of Washington. And they also did a lot of transport and thermodynamic measurement together with our neutron scattering collaborators actually provide a lot of complementary views from many different perspectives. And I also want to thank all the support from the funding agencies. So this is my outline. And I'm going to first talk about the evidence of ground state of the selective monophase in the iron tellurium selenium FTS. Then I'm going to talk about our observation of temperature-induced optoselective mode transitions in these iron pnictides, this lithium iron arsenic. Last, I'm going to talk about the observation of this a geometric flat band pin at the Fermi level by the optoselective electron correlations. So, so I don't think I need to introduce much about the basics of the iron-based superconductors to the audience here. So generally, the iron-based superconductors, the electronic structure is mainly consists of the iron 3D orbitals around the Fermi level. And for the tetrahedral crystal field, split the five 3D orbitals of the iron into T2 T2G and 2EG orbitals with three T2G orbitals, which is the DXC, DYZ, DXY, mainly cross the Fermi level and form these multiple hole bands around the gamma and electron bands around the AM point. And yarn-based superconductors that actually has a lot of different families, and they are in terms of electron correlations, I think there are 2 points. One is that generally the iron chalcogenide possess a stronger electron correlation than iron pnictide. The other thing is that the correlation effect except a very strong orbital dependent behavior with the XY orbital always possess a larger electron correlation than the other d orbitals. And meanwhile, there were so-called these optoselective mode phase predicted in these iron-based superconductors with some finite Hons coupling J and Coulomb interactions U. This so-called OSMP phase means that only the the DXY orbital is completely localized, but with all the other 3D orbitals remain itinerant. And this OSMP phase actually is universally observed in these iron chalcogenide families, no matter whether they are a single crystal or thin films, or no matter what their Fermi surface topology looks like. With increasing temperature, their DXY, the spectral weight of the DXY orbital always vanish, while the spectral weight of the DYD orbital still remain finite at the high temperatures. This is a so-called temperature-induced OSMP phase. But one thing is that for the temperature-induced OSMP phase, it's very hard for us to study the electronic structural evolutions across these OSM orbital selective mode transition, because at high temperature, the spectral weight is going to be very incoherent. The band is the data we got is going to be very fuzzy. We will not be able to really see the clear electronic structural transition. So we want to really look at the orbital selective mode transition that happens at a very low temperature, even ground state. So if you look at the FTS family, we find that if it goes toward the iron tellurium end, the effective mass or the renormalization factor of the DXY orbital increase dramatically, even except a divergent behavior, which strongly indicates that the OSMP at the iron tellurium may happen at the very low temperature, even the ground state. So we took the RPS data at several different dopings from the optimal doped FTS to the iron tellurium end, and this is a gamma M cut we observed, and this is a second derivative data. Two things we find that one is that we find that the bands corresponding to the YZ orbital, the effective mass does not change much with the different dopings, but the effective mass of the XY orbital strongly enhanced towards the iron tellurium end. We can actually fit those band dispersions by the parabolic band and extractive effective mass, and the blue circles are the extracted data. We find that the effective mass actually diverges towards this iron tellurium compound, and we can just take the inverse of this effective mass and the equivalent to get this quasi-particle spectral weight is linearly extrapolate to zero, very close to the iron tellurium region. So this strongly suggests that the iron tellurium is in a has a at least is in proximity to the orbital selective mode ground state. Then this is let's take a look at the Fermi surface mappings. From the Fermi surface mapping, we find a very interesting Fermi surface reconstruction from the optimal doped compound to the iron tellurium end compound, which is that the XY whole band around the Bernoulli center seems to gradually evolve to the X point from a Fermi pocket around the X point. This is very interesting, and we want to know the origin of this evolution. So we take the cut along this gamma X gamma direction for these different dopings, and we this is the second row is corresponding gamma X gamma cut, and these triangular points are actually the fitted band dispersions, and they actually plot the Fermi level and form this dash Fermi surface in this Fermi surface mapping shown. And so this shows that the Fermi pocket around this Bernoulli X point are actually come from these very vertical-like bands along this Bernoulli at this Bernoulli X point, and these vertical bands gradually bend towards this gamma point and form these XY pockets we are familiar with. And then we compare with calculations done by Dongyu and Qimiao, and actually in the OSMP phase, they find that there's actually a z square orbital that cross the Fermi level around this X point, and that's corresponding to the nearly vertical band we find, and this dz square in the correlated matter phase are cut by the XY orbitals and shows a strong, a large hybridization gap at the X point. So this tells us that actually this Fermi surface reconstruction is caused by this dehybridization of this XYZ and the Z square orbitals due to this complete localization of this XY orbital. And we can actually track the hybridizing gap of the XY band and the Z square band and find the hybridizing gap actually close at the iron tellurium end. And then we can compare the Fermi surface mapping we obtained by the RPAS experiment with these theoretical calculations, and they actually match pretty well both in the strongly correlated matter phase and this OSMP phase. And if we recall that we know that when we increase temperature, we can also increase the for example the optimal doped compound into the orbital-selective mode phase. So we actually also compare the Fermi surface at the higher temperature. We find that in the high temperature mode phase, the Fermi surface also matches with the OSMP phase calculations, although the data looks fuzzier. So then I can summarize this part by this phase diagram. In this FTS series, in the iron selenium end, we have a very correlated matter with increasing temperature. At high temperature, we will have a temperature-induced OSMP phase. And when we goes from iron selenium to iron tellurium, we also evolve into a OSMP ground state. And then the coherence temperature from Fs to Ft will gradually decrease. This is also nicely captured by our temperature-dependent data onto a different compound. Okay, this is the first part of my talk. So this second part is I will talk about the temperature-induced OSMP orbital-selective model transition in this iron nictide and this in iron arsenic. So we know that the iron trigonide usually possess a stronger electron correlation than iron nictide. So although there's been a universal temperature-induced OSMT or even ground state OSMP phase observed in the iron trigonide, as far as I know, there is no experimental reports of this OSMP phase in the iron nictides. And if we were to find the OSMP phase in the iron nictides, we want to really look into the crystal that has a strongest correlation among them, which the lithium iron arsenic 111 could be a very good case. And the previous experiments, RPAS experiments combined with DFT and DMFT has revealed that there's a orbital-dependent boundary renormalization, which the DXY orbital has a renormalization factor around 4, and XYZ orbital has a renormalization factor around 3. The temperature dependence experiments also shows that this orbital differentiated the coherence incoherence crossover. That they did the experiment up to 200 Kelvin. Up to 200 Kelvin, they still say the orbital remains a finite spectral weight. So there's no real orbital selective mode transitions with increasing temperature. So then we did our data about up to 300 Kelvin. So this is the low temperature data at the 30 Kelvin and the high temperature data at the 300 Kelvin. And actually, we surprisingly find that the XYZ orbital band remains, but the XY orbital completely disappear. You can see it more clearly from this animation here. This seems to suggest that the lithium iron arsenic also goes into a synthetase with at the sufficiently higher temperature. So we can extract this band from the momentum distribution curves at different temperatures. So this is uh, uh, blue line the low temperature at 30 Kelvin, the high temperature is the yellow lines are MTC at 30 Kelvin. From these MTCs, you can also find that these DXEDYD band still exist, but the XY orbital completely disappear. And we can fit the spectral by two Lorentzian curves and extract the spectral weight, the DXY orbital spectral weight completely disappear at around 250 Kelvin. So this means that the lithium ion arsenic goes into a orbital selective mode transition at around 250 Kelvin. So there's been prediction by Rongyu, Jianwei, and their colleagues say that the lithium ion arsenic is in a orbital selective mode transition phase induced by temperature, but we noticed that this orbital selective mode transition is very sensitive to the Coulomb interactions. We noticed that if we slightly decrease the Coulomb interaction, this whole compound can conveniently enters into a phase without temperature-induced orbital selective mode transition phase. This is actually the case we found in the slightly cobalt-doped lithium ion arsenic. So we find that even if we increase the temperature up to 300 Kelvin, the DXY orbital spectral weight still exists. And yeah, and let me end this part by give you a overview that all the experiments we have done in the iron nictide, we actually find that these for the iron nictide, these orbital selective electron correlations also is universal, and even that there's a lot of almost all the compounds, all the parent compound and then the whole doped compound exhibit these temperature-induced orbital selective mode transitions, except the electron-doped compound. And the last part of my talk is that we find a geometric frustration induced flat band pin at the Fermi level by these orbital selective electron correlations. So the background is that recently the topological flat band from this geometrical frustrated lattice has been very popular. It's under intensive research recent years because of these strongly correlated topology that related to this topological flat band. And also recently we start to study the three-dimensional geometrical fractal lattice, which is the Paraclo lattice. This lattice has an advantage that it's a topological flat band is three-dimensional, but both these two cases there's a issue that we need to tune the flat band to the Fermi level to really get this strongly correlated topology into play. So one strategy we have here is that you can sort of tune this a flat band to the Fermi level with this orbital selective electron correlation effect. Strategy is that these Paraclo bands with this flat band is likely to be more susceptible to the electron correlation effect. So if, for example, if we switch on the electron correlations, the Paraclo bands could be strongly renormalized with this coherent state being very close to the Fermi level, and the incoherence bond is lower Hubble and upper Hubble band. And it turns out this is really the case in the material that it's been called the cobalt vanadium sulfur 124. So this sample, this material has a vanadium Paraclo sublattice and also the copper diamond lattice. If you look at their valence configurations, that the copper atoms are completely filled by the 10 electrons, and the vanadium atoms from this Paraclo sublattice has an average of 1.5 electrons filling the 3D orbitals. So the vanadium bands can really feel this strong electron correlation effect that induced by the Houns's coupling and the Coulomb interactions. And this is the DFT calculations for this compound. And we really find that the low energy states are dominated by the vanadium states, where the coupled state and the sulfur state sits at the relatively higher binding energy, and they have some hybridization with these vanadium bands. And also we find that it's a completely flat, or a very flat three-dimensional flat bands, but it's located about 0.5 eV above the Fermi level. Then we took the opposite data on this compound. We find that actually the high energy bands matches very well with the DFT calculations, which the high energy band is come from the copper and the sulfur band, but the low energy bands deviates from the DFT calculations, that is from the vanadium bands. So then Chen Lei Chen, Qimao student did these calculations which include the correlation effect. So then the particle vanadium bands are strongly normalized to the Fermi level, and we compare these calculations with and without correlations with to our data. We find that the calculation with considering correlation effect matched very well with RPS data. And in this case, the flat band actually shift very close to the Fermi level. And if you look at if we use a relatively smaller photon energy to increase the vanadium photon ionizing cross sections, we can really see the vanadium flat bands that sit very close to the Fermi level, both in plane and out plane. And we can do a very detailed photon energy scan that really shows this three-dimensional flat band. And the flat band is actually pinned at the Fermi level by these orbital-selective electron correlations we mentioned before. And then our collaborator also did this heat capacity and resistivity measurement. They show that there's a very large Sommerfeld coefficient, which presumably comes from the flat band at the Fermi level, and also this long Fermi liquid behavior from the resistivity measurement that shows the effect of the flat band. And then this is my conclusion for all the three studies that we have done. And I think this orbital selective electron correlation effect is universal in this multi-orbital d-electron transition metal compound, not just the iron-based compound we mentioned, also the three-dimensional particle lattice, which has a 3D orbital bands, and also the pnictides. The other thing that I think I learned is that this orbital selective electron effect is not just a consequence or not just a phenomenon of this correlation effect in a multi-orbital system. I think it's also a driving force. So it can induce these Fermi surface reconstructions, and it can pin the flat band to the Fermi level. So then it can be more related to the superconductivity and the ferromagnetism or the other exotic phenomena in these material resistance. And that's all for my talk. Yeah, thank you for the attention.
Thank you very much, Jianwei, for going through all this material. Very nice talk. Any questions anyone has? Fang?
Hello, can you hear me?
Yes.
Yeah, very nice. I want to ask one very simple question. So in the iron, tellurium, selenium compound, so what is the effect of X here? Since they're in the same group, I think they don't change the filling factor, right?
Sorry, can you what's the effect of what?
X, the doping level X. I think here it's not changing the electron density, but
yeah, it's I think it's changing the ion the bond angle and the bond height. So it will change the hopping between the ion and the pnictide ion. Yeah.
Thanks.
Christine?
Hi, very nice talk. Thank you very much. I have sort of two related questions. And first one is that I want to clarify again, like, what is the relationship between the MOS transition, the orbital selective MOS transition, and the appearance of the Z square band on the Fermi level when you are going to the 100% tellurium side? And then also I want to know, like, when you're going from 50% tellurium to 100% tellurium, is like because like what you see is that the XY band being completely in plane, like gradually change into the Z square band that is completely out of plane. It's like a gradual transition, or it's like all of a sudden it just change the orbital character.
The second question from the experimental data, I think it's a gradual transition, but I'm not sure from whether the calculation can produce a gradual transition in this case. But I think if we tune these correlation strengths, I suppose this hybridization gap can be gradually shrink. So I don't know. From the calculation, it seems to be a very sudden change from only from the experimental, you can see there's a gradual change. I'm sorry, what's the first question?
The first question, I just wanna like maybe I missed that point that you explained, that what is the relationship between the orbital selective mode transition versus the appearance of like you have this Z square band crossing the Fermi level? And does it mean that the XY band just completely disappeared and you all of a sudden just seeing the Z square band?
Yeah. Just because these XY band just completely disappear. So then these square band will cross the Fermi level and form this band around this variable X point.
Okay, thank you. Very nice work. Thank you so much.